So this exercise is directly related to our rocket project Ad Astra, and this is something that scientists, physicists use to diagram forces acting on anything, right? So this is all about forces. You know what I'm saying? Forces, pushes and pulls on our rocket, right? Very important to understand and to be able to analyze and then calculate. So, in able to analyze forces, we use the tool called a free body diagram, right? A free body diagram. Free body diagram, right? So, what it really does is it just analyzes an object and all the forces acting on it, and then we look at those forces, and forces are vectors, so in each direction those forces are pushing and pulling, and see if there's a net force, which means does one force win out overall, and what direction or directions will that accelerate the mass to? Because we do know Newton's second law says force is equal to the mass times the acceleration, right? So this relationship will govern how our object moves, right, in real life. So I'm going to go ahead and, first of all, diagram you just a quick object, and this object could be anything. It could be a cat or a football or whatever. But in the middle, we put our mass, and I'm going to have something that has 5 kilograms of mass, right? Now, some forces could be acting on this, right? But I don't know them. I have to sort of analyze the situation in real life, right? Maybe in a problem it might tell you, or maybe when you're working on your rocket, you just have to sort of like think about what's happening when the rocket is sitting on the table or when it's flying through the air or anything like that, right? Forces may be acting on it. So let's compile here a list of possible forces that might be acting on it, right? So, of course, we have the force of gravity, which you guys already know about, right? So we can call that F sub g, the force of gravity, right? So gravity. And we have, let's say, the force of maybe friction, right? The force of friction, right? If I push it along the ground and the ground is rough, right? The ground, I misspelled friction. The ground might not be smooth, and the thing that I'm moving it on might not be smooth, and those roughnesses will make it like catch against each other and provide friction. That's that scraping sound that you hear when you like drag a table across the floor. That's friction, right? So there are other types of friction too, like air resistance. Like if you're like swinging a tennis racket, you hear that whoosh, right? The air is pushing back on you. That right there is we call drag, right? When we might call that drag, right? You're dragging something through the air. You see this a lot in aeronautics, right? So air resistance we call drag. Drag. That's a new one, right? Drag. A whole bunch of other forces can act on something, right? Another force that can act on something, and especially rockets, is thrust, right? Thrust. And I can say that's F sub t, and that would be thrust, right? Really, you can use any F sub whatever you want, as long as it makes sense and as long as you define it to me. Like, hey, Mr. Jennings, F sub t is the thrust of the rocket, right? And where does the rocket get thrust from, right? Where does that force come from? So when you've designed your water rocket, right, hopefully you followed the proper instructions and put the nozzle on the bottom of the bottle, right? So the thrust is going to come when we introduce pressurized air and a little bit of water inside this container, and it gets all pressurized. And then quickly we release a little mechanism that I have that's going to expel that. And guess what happens? All that pressurized gas goes down, right? And the equal and opposite effect of that is the rocket goes up, right? Up, up. So the thrust, right, would be, I guess, down in the downward direction, right? So we might have some thrust on this rocket, right? We could also have pushes and pulls on it, right? So what if we had, like, I might say, a force that's wind? Wind is like acting on it, right? So if I launch my rocket in the air, maybe the wind is blowing in a certain direction, maybe left to right or east to west, and that would affect, the acceleration of the rocket as well, where it's going. So all these forces are on the rocket, right? Let's say that it's not moving though, and it's on the ground, right? Are there still forces acting on it? Sure there are, right? Gravity's still acting on it no matter what. But how come it's not falling through the earth? Well, we have another force on it that we call the normal force, right? And the normal force is exactly proportional to its gravitational force, right? The normal force, it's called the normal force because it is what is counteracting gravity, right? It is keeping you upright, and that's why we call it the normal force. It's normal, it's everywhere, right? So anything that's not moving and sitting down on like a table or whatever, that table's pushing back up against it, and the normal force is the amount of that force, right? So we have all of these forces on it. We have our diagram with the mass in the middle. Now we can start looking at forces. Now I'm just going to create a few scenarios, right? So I'm going to select some arrows. Let's see, some arrows here. And let's say that I'm pushing a box along a table, right? I'm pushing a box along a table, right? So let's say I'm pushing the box, and the box is being pushed this way, right? Well, you can imagine the table is not completely smooth. There's going to be some friction there. So the friction is going to be going that way, right? Counteracting the box, right? And I can label these. Watch me label them. So here's my push force, right? And I can say that's the force of the push, right? So that's my push force. And, that's not on here, but, I can put it on there, right? FP push. Maybe that's a push force. And counteracting that would be my friction force, right? So I have my push force and my friction force. What about up and down? Well, down, you should already know that I have my gravitational traction between the box and the earth, right? This is also called something else, right? It's called the weight of the box, right? The weight of the box. So the weight of the box is pulling down, right? And we can call that F sub g, gravity, right? Or we can call it weight, right? The weight of it. So the F sub g, the weight of it, the force of gravity, whatever. And we also have something pushing back up, because it's not falling, is it? It's not falling through the table. The table's pushing back up, and we have our normal force, right? Our normal force. Our normal force. And let's label that one. So we have our normal force, F normal. The normal force. All right, so we've got our friction force, our push force, or pull force. We've got our normal force and our force of gravity, right? So you have to look at all these by itself, right? By itself in the situation. Something I'm always going to know is this gravitational force, right? Because I can solve it with F is equal to ma. F is equal to ma. So what is the force acting on this? Well, all I have to do is use Newton's laws and solve, because I actually know two of these things, right? I don't know the force being pulled down, but I do know the mass, which is 5. So I know that force is equal to the mass, which is 5 kilograms, times the acceleration, which is a. What is the acceleration due to gravity on Earth? You should already know that it's negative 9.8, right? You always know that. Negative 9.8 is always going to be there for you. So all I have to do to find the force of gravity on something, or that something's weight in newtons, is multiply its mass times acceleration. That's Newton's second law. That's why we learned it. So all you have to do is break out your calculator and then multiply for the mass, which is 5, times the acceleration due to gravity on Earth. 9.8, right? 9.8. So 5 times 9.8 is equal to 49, right? Almost 50. So that's equal to 49 newtons. 49 newtons. So the force of gravity is 49 newtons. Newtons, right? All right. So what do you think the normal force has to be? It's not moving down and it's not moving up. So it has to have an equal and opposite reaction. So the normal force is 49 newtons, which is why it's normal. It's normal force. It's always going to be the same as something's weight, right? Because it's what's propping up something's weight. The floor is pushing back up on you, right? So we have this cool normal force. Now it gets tricky. So what is the net force? So this is negative, right? I've neglected to put that because 5 times negative 9.8 is negative 49. The normal force is going to be positive 49 because these are vectors. They have directions, right? Gravity pulls down, the normal force pushes up. So if this is negative and that's positive, guess what? It nets out to 0, right? So we have up and down a net of 0. Now that wouldn't be the case if it was too heavy for the chair and the chair broke. Then there would be a net force. The gravity would take over, and that would be what's winning, and this would be 0. But that's not the case here. So let's say here that I have a push force, right? I'm pushing this box, and I'm pushing it with a force of 10 newtons, right? And the friction force is 2 newtons, right? There's 2 newtons of friction force. So my question is, what is the net force acting on this box, right? What is the net force acting on this box? And what is the acceleration? What is the acceleration of the object? You should be able to see what's going on with this object if you have a trained eye, you know? So just looking at this, I'm going to change the color of this real quick. Just looking at this, I have diagrammed 4 forces. I have one here, I have one here, I have one here, and I have one here, right? So I've got one going up, one going down, one going to the right, and one going left. What way, just looking at this, do you think the rocket is going to move? Take a second. If you say it's going to move to the right, you're correct, right? It's going to move to the right. Why? Because there's a net force acting on it, right? One of these forces is bigger than all the other ones, right? This one and this one cancel each other out, and this one and this one don't cancel each other out. 10 is much bigger than 2, right? So it's going to move to the right. It's going to accelerate to the right. But what is the net force? It's not going to be 10. Guess what it's going to be, right? I have to look at the directions. They're opposite, so I subtract them, right? This one is going to be a negative, and this one is going to be a positive. So the difference between them is 8, right? 8 newtons. 8 newtons. There's 8 newtons of net force on this to the right. So that's easy enough. But what's the acceleration of the object? How fast is it going to accelerate? At what rate is it going to accelerate? And I can answer that. My acceleration is going to be found quite easily. I just use F is equal to ma, right? So F is equal to ma is going to tell me the answer to the acceleration of this box, right? So if I got F is equal to ma, I know the net force is going to be 8 because I had to subtract 2 for the friction, right? The friction force. And that's going to equal the mass, which is 5, times the acceleration, which I don't know. Now, it's easy to confuse, like, I thought acceleration was 9.8. No, acceleration down is 9.8. We're talking about the acceleration right when I push it, right? Right? So we need to find out that. Like, if I'm pushing this chair, it's not going through the ground. The normal force is pushing it back up. But if I'm pushing it, there is some acceleration to the right, rightwards, right? And I can find this out by essentially just doing a quick little bit of math, right? So I figure out 8 is equal to 5 times A. A is some number, right? And if I divide both sides by 5, I will figure out what A is. A is remaining, and it equals 8 over 5. And 8 divided by 5 is 1.6, right? So 1.6 meters per second squared, right? And you're going to be able to do this relatively easily once you know all the information, right? So again, it's super, super easy. I want you to go ahead and save this in your notes. Go ahead and stop the video, pause your video, take a picture, whatever you need to do, because we're going to move on. What if we're trying to diagram our rockets now, right? So let me just do a brief little cool rocket design. Let's put the nose cone on there. Nose cone. That is for, boom, aerodynamics, right? To reduce the drag. And we have here our rocket fins, right? To make it aerodynamic, right? Again, further reduce drag and help it go straight. And then we have our nozzle here, and that's going to shoot stuff out the bottom. All right, so let's say we launch our rocket. Boom! Real quick, tell me what force this is. If you said thrust, you're correct, right? The force of thrust. Now, what is counteracting thrust, right? If this thrust vector is going down, right? So let's use a arrow. if this force vector is going down, right, thrust, what is counteracting that? What do you think is going to counteract that thrust? Think about it, right? The rocket pushes down, that's thrust. What do you think, is anything going to stop it, right? Is anything going to stop it? I think so. And I also, let's see. There we go. This is more correct. Okay. Here we go. So that thrust is going to, make the rocket go up. So we'll call it F sub t, the thrust. What do you think is counteracting it? Well, in the Earth, we have an atmosphere made of air, right, which is oxygen, argon, nitrogen, all this kind of stuff. And, a rocket has to actually move through it, right? Like it's a gas. So it's going to provide drag, right? F sub d, the drag, right? The drag. But that's not all. That's not all. There's going to be another force acting on it. And you should already know, Mr. Jenkins, you forgot this force. What is that force? Well, the gravity is also going to act on that. Gravity is also going to act on that, right? F sub g, F sub g, F sub g. Oop. Force of gravity. So I'm going to get my force of gravity on there. Boom. Like this. F sub g. And let's say our rocket is 2 kilograms, right? It has a mass of 2 kilograms. Again, F is equal to ma. Objects at rest will remain at rest. Cool. But objects in motion will remain in motion. Awesome. That's first law. Second law, F is equal to ma. Third law, for every action, there's an equal opposite reaction. All apply. Now, how can I start off? I want you to first start your diagrams by actually and 100% truly understanding that the weight of the object is a force, right? And you can solve that easy with F is equal to ma. How do I do that? How do I find the force of gravity? What is this? All I have to do is take my mass of 2 and multiply it by acceleration, right? My mass is 2, and my acceleration was what? Negative 9.8. Yeah. So what is 2 times negative 9.8? That is going to be what? Almost 20, right? 2 times 9.8, and that's going to be 19 and a half, almost 19.6. So negative 19.6 in the downward direction. That's what that negative means. 19.6. So the force of gravity is equal to 19.6 newtons, right? So what do you think the force of thrust has to be? Well, it's got to be more than 19.6 newtons, right? Or else we're not going to take off. We're not going to lift off. So I want you to create me a free body diagram, and we don't know how much the drag is going to be, right? But if it's too much, it's definitely not going to move, right? This can't be, this one and this one cannot add up to 19.6. Or this one and this one have to beat 19.6 because we're trying to lift off this crazy planet and get the heck out of here. So I want you to go ahead and do some calculations for you. Now, what is the mass of your rocket? What is the mass of your rocket? Your rocket. What is the mass of your rocket? Well, I want us all to use the same number, and I want you to assume that when we have air and water and all the tape and cardboard, that your mass is equal to 4 kilograms. And I want you to take that, and I want you to follow the instructions on this activity, and I want you to create me some diagrams and submit them to me with some calculations. Follow all the instructions. You can come back and watch this video on this, and I will have, of course, F is equal to ma there for you. That's the sample calculations right there. I want you to follow the instructions on this next activity exercise and complete the free body diagrams that I ask of you and use F is equal to ma to calculate those forces. All right, y'all. Thank you very much, and continue on to our story building exercise right after this one. Thanks, guys. Bye.